Hey folks, we're going to do another example of electric fields caused by charge distributions, and this one is probably the easiest one we'll have, and that is a ring of charge. So imagine that you have a full ring of charge, and there's an axis that runs through the middle of it, okay, and we want to know what's the electric field here, some distance away from the center of the ring of charge, along that axis. So some things that we would know, let's say the radius of the ring is capital R. Let's call this distance here d between the center of the ring and the point we're looking at. And we're going to figure out the electric field created by the ring at that point. So I hope that if you look at this, you would notice the following. Let's say there's a dq up there. It's one of our electric field or one of our charges. If that, assuming it's positive, that little charge would make a dE pointing that way, right? Well, if I had another little dq down there, that's going to make a field pointing that way. So we'll call that the dE2. Okay. If I had a dq here, let's say, that's going to make a field. Now this one's tough to draw. It would be to the right and into the page. And if I had a dq there, that would make a field to the right and out of the page. Well, hopefully what you notice is the following. All the ups, downs, lefts, and right, or I'm sorry, all the ups, downs, into, and out of pages cancel. And the only part of the electric field that actually adds together is the horizontal component, the x component. Okay. So our base equation is integral E equals the k integral dq over r squared in the r hat direction. Well, in this case, for r hat, all we want is the horizontal component of each of these little guys, which is going to be cosine of theta. So the electric field would be k, the integral of dq over r squared cosine of theta. Okay. Now, we've got three variables here. We've got a dq, we've got an r, and we've got a theta. But it turns out that two of those three things aren't really variables, all right? So let's start with the angle and the radius, actually. So the radius is from any particular dq to our point. We'll call that little r. Well, if you look at that, no matter which dq I pick, that little r is always the same. Matter of fact, what does that equal? Little r equals the square root of big R squared plus d squared, right? It's a right triangle here, and little r is the hypotenuse of that little right triangle. And how about cosine of theta? Okay, well, that's really simple. Here's your angle right there in that right triangle. And the cosine of it is d over little r, which is d over square root of r squared plus d squared. Okay, so I am going to plug this in for cosine theta, and I'm going to plug this in for little r. And look what we end up having left. You get E equals K, the integral of dq, still haven't done anything with that yet, over square root of big R squared plus d squared simply equals r squared plus d squared, times cosine of the angle, which is d over square root of r squared plus d squared. Okay, d is a constant, as is all that. So we can pull all that out of the integral. We got k times d. If I combine these, they turn into r squared plus d squared to the 3 halves. And what are we integrating? dq. Well, hello, what's the integral of dq? Well, it's just q. And so you get the following equation. The electric field is equal to k. I'll write the q first, and then d. D is your variable, so I'll put that at the end there. And then you get r squared plus d squared to the 3 halves, okay? So there's your answer. And that's in the x direction. That's to the right, okay? There is no field up, down, into, or out of the page. Now, one last thing, I want to make a note of this. If you get really far away from this ring, it should look like a point charge to us, okay? In other words, in this equation here, if I make d much, much bigger than r, then this equation should look like that of a point charge. Well, if you make d much, much bigger than r in the denominator here, you ignore the r squared. When you're adding two numbers that are hugely different, you ignore the smaller one. And so E would be approximately KQD over, so if I ignore the r squared, it's just d squared to the 3/2, which is d cubed. And that reduces down to KQ over d squared, which is like a point charge KQ over r squared. All right, so that was the easy one. Don't worry, they'll get harder again. So I hope you enjoyed that and have a good one.